Hi everyone, and thank you for listening to my talk. My name is Rebecca Martin, and I'm from the University of Nevada, Las Vegas. Today, I'll talk about the dynamics of misaligned disks in and around binary star systems and implications for planet formation. This includes protoplanetary disks around one or both components of a binary, and also circumplanetary disks that are around forming planets. And the forming planet is essentially one component of an extreme mass ratio binary. I'll try to explain the theory of the dynamics of misaligned disks and their interactions with planets that form within them. So why are we interested in binary stars? Well, most stars are in binaries. So understanding the planet formation process both in and around binaries is essential for us to understand the observed distributions of exoplanet properties. For example, in the Kepler sample, around 40 to 50% of the planet host stars are in binaries. Both the protoplanetary disk and the planetary system itself are affected by the secular torque from a binary companion. So in this talk, I'm going to focus on the dynamics of protoplanetary disks that help us to understand at least the formation conditions for planets. Misalignments between disks and their binaries are commonly observed. They're seen in circumstellar disks, meaning the disk around one component of a binary. And here I've got two examples of binaries with a disk around each component. And in each case, you can see that the disks are highly misaligned to each other. The upper panels show HK Tori that has disks that are misaligned to each other by at least 60 degrees. And the lower panels show V2434 Ori. And the angle between the projected disk rotation axes is 72 degrees. Misalignments are also seen in circumbinary disks, meaning the disk that orbits around both components of a binary. And there's a couple of examples here on the right. First, there's the binary protostar IRS43. This has a circumbinary disk and circumstellar disks around each component. The dashed lines in the image show the cross-section of the three disks, and you can see that all of the disks are misaligned to each other. The image on the far right shows HD98800, and this disk is misaligned by almost 90 degrees to a central binary. So generally, misalignments are seen for wider binaries with orbital periods greater than about 30 days. Stochastic processes such as turbulence during the early phases of star formation are thought to drive the disk misalignments. The images on the right here are from an SPH simulation by Matthew Bate in 2018. And we see large misalignments between disks around the binary components. Stellar flybys can also potentially lead to misalignments. Circumplanetary disks form around a giant planet that's forming within a protoplanetary disk. Once the planet reaches a mass of about Neptune, it opens up a gap in the protoplanetary disk, and the continued infall of material forms a circumplanetary disk around the young planet, as shown in the lower left image here from an MHD simulation by Grezel et al. And they found that circumplanetary disks can form with a slight misalignment of up to about 15 degrees to the orbital plane of the planet. Now, this talk is divided into three main sections. I'll first describe the dynamics of circumstellar disks, and then I'll move on to circumbinary disks. Finally, I'll discuss the planet-disk interactions in these dynamically evolving disks. Okay, so first I'm going to begin to consider the evolution of a circumstellar disk at low inclination. So this is relevant both for protoplanetary disks in binaries and also for circumplanetary disks. So let's first consider the dynamics of a test particle in order to understand the dynamics later of a misaligned circumstellar disk. So here I have a sketch of a binary that has a slightly misaligned test particle orbiting around one component. Now, the tidal torque from the companion star has two main components. The m=0 component causes retrograde nodal precession of the test particle orbit. I tried to describe this in the lower right sketch. So the purple upright vector describes the angular momentum of the binary, while the blue vector describes the angular momentum vector of the particle orbit. So the angular momentum vector of the particle orbit precesses around the angular momentum vector of the binary orbit. The second important part of the torque is the m=2 component, and this causes a wobble on a timescale of half the orbital period of the binary. The wobble doesn't affect the average nodal precession rate, since the precession timescale is much longer than the orbital period. So now we understand how a particle behaves. Let's apply this to a misaligned disk. Now, the gas in the disk feels the same torque as the test particles, but each ring of the disk in isolation wants to precess on a timescale that depends upon its radius from the central star. The closer to the perturbing star, the faster the precession rate. However, the precession is communicated through the disk by waves that propagate at half the sound speed. So in order for the disk to precess as a solid body, we require the sound crossing timescale of the disk to be smaller than the global disk precession timescale. If this condition is not satisfied, then we get disk warping or potentially even disk breaking. For a disk around one component of a binary or a circumplanetary disk, we generally have solid body precession. Circumbinary disks, on the other hand, may be sufficiently extended to undergo breaking. Since the disk precesses like a solid body, it undergoes the same dynamics as the test particle, but on a global scale. The timescale for the precession is a density-weighted average of the timescale of the individual rings in the disk. So the disk undergoes retrograde nodal precession with a wobble on a timescale of half the binary orbital period. Now, a big difference between the dynamics of a test particle and the dynamics of a disk is that the disk has viscous dissipation, and this can lead to tilt evolution. Now, the two main components of the tidal torque have competing effects when it comes to the alignment of the disk. In the presence of dissipation within the disk, the m=0 term, or the nodal precession term, leads to coplanar alignment. The disk angular momentum vector gradually spirals in towards alignment to the orbital angular momentum. So in this case, the disk moves towards coplanar alignment to the binary orbital plane. However, the m=2 term, or the wobble term, has the opposite effect and instead leads to tilting. In this case, the inclination of the disk gradually increases while the disk precesses. So depending on the relative strength of these two competing effects, the disk may become more or less aligned over time. For a circumstellar disk, the outcome is generally alignment. However, for circumplanetary disks, the outcome for reasonable disk parameters is in fact tilting. And this is because circumplanetary disks have a small size and a large disk aspect ratio. So for some typical circumplanetary disk parameters, the image on the left, we solve the one-dimensional linear time-dependent warp disk equations. So the plot on the left shows the tilt and the nodal phase angle of the disk as a function of time. the disk displays retrograde nodal precession and its tilt gradually increases. You can also see the m equal to 2 component operating, as this is causing the small oscillations during the tilting. This 1D model assumes a fixed surface density profile. So in order to allow the surface density to evolve in time, we need to use 3-dimensional hydrodynamical simulations. So on the right, I show you some examples of these with both a grid code and with SPH. And the upper 2 lines show Athena++ simulations, while the lower 3 show phantom simulations. So these simulations are in pretty good agreement with each other. And again, they allow the disk to have a surface density profile that's tidally truncated by the star and also evolving in time. The different lines for the simulations just show different resolutions. And the differences between the 2 codes are likely a result of slightly different surface density profiles in each. However, they show similar behavior to the 1D model on the left. Just note that the different time axis on the left and the right panels. So the conclusion here is that the circumplanetary disk is unstable to tilting for reasonable disk parameters. So far, we've only considered the dynamics of the circumplanetary disk itself. But now let's explore the effect of this circumplanetary disk evolution on a spinning oblate planet. Now, the spinning planet exerts a torque on the disk, and the disk exerts an equal and opposite torque on the planet. So the sketch on the right, the blue arrow shows the disk angular momentum vector, while the red arrow shows the planet's spin angular momentum vector. And the green arrow is the sum of these two. So in the absence of the star and dissipation in the disk, the circumplanetary disk and the planet's spin precess about their total angular momentum vector. So the size of the oscillations of each depends upon the relative magnitude of the angular momentum of the disk compared to the spin angular momentum of the planet. So in this example, the planet's spin has a larger angular momentum than the disk, and so undergoes smaller oscillations. If we include disk dissipation, then the planet's spin and the disk spiral inwards and both align towards the total angular momentum vector. So what happens now if we include the effects of the star? So now we include the planet torque into the same 1-dimensional simulation. Now the left panel here is the same as the figure that I showed before without the planet torque, where you see that the disk is unstable to tilting. And the right panel shows the same circumplanetary disk model, but includes an oblate spinning planet with a quadrupole gravitational harmonic J2 of 0.01. And this is similar to Jupiter and Saturn in the solar system. And the mass of the disk is 1% of the planet mass. The blue lines show the disk and the red lines show the planet's evolution. Now the planet spin and the disk precess around each other on a timescale of about 3 planet orbits. And because of dissipation in the disk, they align to each other on a timescale of about 20 planet orbital periods. On a longer timescale, the tilts of both increase. The tilt growth timescale is longer than for the disk without the planet torque on the left, but it's still relatively short in this case. Disks around planets that are farther away from their star have a larger Hill radius, and therefore they may extend farther from the planet. This means that they can potentially have a higher angular momentum. A circumplanetary disk with a higher angular momentum is able to tilt the planet's spin axis on a shorter timescale. So we expect planets that are farther away from their host star to be more easily misaligned with this mechanism. And the formation of satellites from a misaligned disk may be quite different to a coplanar disk. Right, so far we've just considered low inclination disks. Now let's think about what happens if we have a more highly misaligned disk. Again, it's useful to consider what happens with a highly misaligned test particle. Now, a test particle with an initial inclination greater than about 40 degrees is unstable to Kozai-Lidov oscillations. This is an example shown here where the test particle is initially misaligned by 60 degrees to the binary orbital plane, and the inclination is shown in the lower panel here. And the particle orbit is initially circular, as you can see from the eccentricity panel at the top. But the Kozai-Lidov oscillations exchange the particle inclination and eccentricity. So a peak in the eccentricity corresponds to a trough in the inclination. The timescale for these oscillations depends upon the orbital radius from the central star. So the closer the orbit is to the central star, the longer the timescale. So we understand how the test particle evolves, but how would a gas disk evolve? This shows a three-dimensional hydrodynamical simulation, again using phantom, and we consider the evolution of a highly misaligned disk. The disk is able to hold itself together and undergo global Kozai-Lidov oscillations, rather than each radius undergoing these oscillations on a different timescale. But you can see that the eccentricity and inclination evolution is somewhat different to the test particle case, and that's because there's dissipation in the disk. So the oscillations are damped rather than being periodic like the test particles. The disk inclination damps down to the critical Kozai-Lidov oscillation inclination. But note that this critical inclination is not the same as in the test particle case. So for the disk, it's highly sensitive to the disk aspect ratio. And in this case, you can see that oscillations are indeed taking place below an inclination of 40 degrees. Now, there are several ways that highly misaligned disks that are unstable to these Kozai-Lidov oscillations may be formed. The disk in a binary star system may already form with sufficiently high inclination to undergo these oscillations. Circumplanetary disks, on the other hand, are unlikely to form with such a high inclination, and they're going to form close to coplanar. However, as we've already seen, circumplanetary disks are unstable to tilting, so the inclination can increase sufficiently that they become unstable later on. The plot on the lower right here shows the eccentricity and inclination of a circumplanetary disk. In the lower panel, you can see the disk tilt increases until it becomes Kozai-Lidov unstable. And then at this time, you see a large increase in the disk eccentricity while the inclination drops. Now, during the high eccentricity phase, the accretion rate onto the planet increases. So a disk that's undergoing Kozai-Lidov oscillations shows episodic accretion. And this could have implications for observations of forming planets, since they periodically may have a higher accretion rate. When we have a circumbinary disk, it feeds the formation of circumstellar disks around each component of the binary. If the circumbinary disk is misaligned, this then provides a source of high inclination disk material. The circumstellar disks that form can then both undergo Kozai-Lidov oscillations. The plot on the right-hand side here shows a simulation with a circumbinary disk that's misaligned by 60 degrees. Its inclination is shown in the dotted line. The solid lines show the evolution of one of the circumstellar disks. The disk inclination and eccentricity are exchanged in these Kozai-Lidov oscillations, and the constant supply of highly inclined material from the circumbinary disk allows the circumstellar disk to undergo long-lived Kozai-Lidov oscillations. So these highly eccentric disks may have significant implications for planet formation around each component of a binary, since planets may form or at least begin to form in a highly eccentric disk. If the disk is sufficiently massive to be self-gravitating, then the cosine of oscillations may be weakened or even suppressed. These plots show the eccentricity, inclination, and disk mass evolution for 3 disks of varying mass. The left panel shows simulations without self-gravity, and here we see that all of the disks are undergoing cosine of oscillations. However, in the right panels, we see the effect of including self-gravity. The most massive disks shown in the blue lines, and you can see in the upper panel that the disk remains close to circular. The disk is 3% of the binary mass in this case. However, the smaller mass disks still undergo the oscillations. And so, since we expect the disk mass to decrease over time, eventually the disk will undergo these cosine of oscillations. Now, the highly eccentric disk will certainly influence the planet formation process. Planet formation by disk fragmentation may be more likely in a disk that's undergoing these cosine of oscillations. These images show a simulation with a disk that's becoming highly eccentric over time. The disk is stable against fragmentation without the effect of the binary star companion. However, the cosine of oscillations cause shocks in the disk, and this may aid disk fragmentation. So planets in highly eccentric disks may potentially form through disk fragmentation. Let's move on now to consider the dynamics of a misaligned circumbinary disk. Again, it's easier to understand the dynamics of a test particle orbit first. So the misaligned particle undergoes nodal precession, as in the circumstellar case. For a circular orbit binary, the precession is always about the angular momentum vector of the binary. And the sketch in the lower right shows the particle angular momentum vector in blue. That's nodally precessing about the binary angular momentum vector shown in purple. In the phase diagram on the left-hand side, the distance from the origin is the inclination of the particle orbit, and the azimuthal angle is the nodal phase angle. For a circular orbit binary, the precession has a constant inclination, and so we see circles in this phase diagram. Each line represents a test particle orbit that's nodally precessing with a different initial inclination. The green lines show orbits that are closer to prograde, and the blue lines show orbits that are closer to retrograde. So these precess about the negative angular momentum vector of the binary, as shown in the sketch on the right. Now, the timescale for the precession depends upon the orbital radius of the test particle from the binary. The farther away the particle is, then the slower the precession. Now, if instead we have a circumbinary disk around a circular orbit binary, again, it undergoes retrograde nodal precession. However, because of dissipation within the disk, the inclination gradually decreases and the disk moves towards coplanar alignment to the binary orbital plane. Depending on the initial misalignment, the disk can move towards prograde or towards retrograde coplanar alignment. Now, as I mentioned earlier, if the disk is sufficiently extended, it may be subject to disk warping or even breaking. In this case, different parts of the disk may precess and align on different timescales. I'd just like to briefly explain what the binary eccentricity vector is. In this sketch, the binary is orbiting in the xy plane, and so the angular momentum vector is in the z direction. The eccentricity vector points in a direction towards the periapsis. This means it lies at 90 degrees to the binary angular momentum vector and along the x-axis in this case. So going back to the test particle orbits, and now considering an eccentric orbit binary. So the test particle orbits are now much more complex. The diagram on the left again shows this phase diagram where the distance from the origin is the inclination of the particle. So for low inclination orbits, shown by the green lines, the precession is again about the binary angular momentum vector, which in this diagram is at the origin. However, for larger initial tilts, the particle doesn't precess about the angular momentum vector, but instead is precessing about the binary eccentricity vector. So in this phase diagram, the eccentricity vector is at 90 degrees to the angular momentum vector. So these are librating orbits centered on the eccentricity vector. And let's look at in one of these in more detail. So I've highlighted this purple orbit that has an initial inclination of 60 degrees. So here we see the inclination and nodal phase angle as a function of time for that orbit that begins at 60 degrees. The inclination shown in the upper panel oscillates about 90 degrees, while the phase angle librates. This just means it varies over a small range of values. The solid and the dashed lines show particles at different orbital radii. Now the dashed line is for a particle that's farther away from the binary than the solid line, and so the dashed line is undergoing the same oscillations but on a longer time scale. Now, instead of a test particle, let's consider a disk. Then viscous dissipation leads to tilt evolution. If the circumbinary disk is sufficiently narrow and warm, then it's able to precess as a solid body in a similar way to the circumstellar disk. The disk then aligns to one of two possible outcomes. So for small initial misalignment, it moves to coplanar alignment, while for large initial misalignment, it moves towards polar alignment. And I'll show this now with some hydrodynamical simulations. This plot shows the inclination and nodal phase angle evolution for a disk that begins at 60 degrees around an equal mass binary with an eccentricity of 0.5. We see the tilt oscillations similar to the test particle case, but now they are damped. The disk is moving towards what we call polar alignment. In a polar aligned state, the disk is perpendicular to the binary orbit, with its angular momentum vector aligned to the eccentricity vector of the binary. The dashed and solid lines in this plot show two different radii in the disk, and you can see that they're quite similar because the disk is behaving as a solid body. This shows an image of the disk at the end of the simulation when it's getting close to polar alignment. The binary orbit I've sketched on the top, but it's not shown to scale. The disk is perpendicular to the binary orbit, with the angular momentum of the disk being close to alignment to the binary eccentricity vector. And this is a stable state. Recently, Ian Rabago, who's a graduate student working with Zhao and Zhu at UNLV, has run some grid code simulations with Athena++ of a precessing circumbinary disk with a high initial misalignment. So in this movie, the binary angular momentum vector is upwards, meaning the binary orbits in the horizontal blue plane. The binary eccentricity vector is along the white gap in the plane. And you can see that the disk is precessing about the eccentricity vector during the simulation. So while running such simulations in a grid code is numerically quite challenging, The advantage of using a grid code over SPH is that we can consider much smaller viscosity. And this figure shows the phase diagram for 3 different disk viscosities, and we see that aside from some initial adjustment, they're actually quite similar. This is a work in progress, so look out for it in the future. We can also solve the wave-like warp disk equations and find that the simulations agree well with linear theory. The upper plot here shows the precession period as a function of the disk in a radius, as predicted by linear theory. And the black dot shows the hydrodynamical simulation. And the lower panel shows the tilt decay timescale, meaning the timescale on which the disk moves towards polar alignment. And again, we find good agreement. So polar alignment occurs at 90 degrees to the binary angular momentum vector if the disk has a small angular momentum. However, if the disk has a significant angular momentum compared to the binary, then the polar aligned state is no longer at 90 degrees, but actually occurs at lower levels of tilt. This plot shows an analytic determination of the stationary inclination as a function of the ratio of the disk angular momentum to the binary angular momentum. So each line shows a different binary eccentricity. The stationary inclination decreases with increasing angular momentum ratio. So the points show the results of 3 body simulations. They're actually in very good agreement with the analytic curve. So from disk observations, if we know how old the disk is and we know there's been sufficient time for alignment to have occurred, then observing the misalignment of the disk, which may be just a few degrees away from 90, for example, this could help us to constrain the mass of the disk. Recently, the first polar aligned gas disk was observed with ALMA. HD 98800 is actually a quadrupole star made up of 2 binaries orbiting each other. There's thought to be a polar gas disk around one of the binary components. The observations show that the disk could be misaligned by either 48 degrees or 87 degrees. Kennedy et al. Used dynamical arguments to show that the disk alignment must be polar, since if the disk began at 48 degrees, the polar alignment timescale is very short. It's unlikely we would see it at that inclination. And more recently, we showed that the disk inclination can be determined by the observed cavity size. So the binary at the center of the disk clears out a hole in the inner parts of the disk, and the size of this hole is very sensitive to the binary inclination. These 3 images show hydrodynamical simulations at different inclinations. So on the left, the inclination of the binary is coplanar, in the middle it's 48 degrees, and on the right it's 90 degrees. It's in a polar configuration. So the cavity size is significantly smaller in the polar aligned case shown on the right than it is at 40 degrees in the middle. So the small hole size is actually in agreement with the observations, suggesting that the disk is at the 87 degrees, being close to polar, rather than at the 48 degrees. We've also seen polar circumbinary disks in more evolved systems. 99 Herculis is a polar ring debris disk that's been observed with Herschel. The binary eccentricity is very high at 0.77. Hydrodynamical simulations show that even an initially small misalignment, a circumbinary gas disk can move towards polar alignment. The plots on the right show a simulation in which the disk begins at 30 degrees, as shown in the upper panel, and moves towards polar alignment on a timescale much shorter than the gas disk lifetime. So the debris that's observed must be small enough either to move with the gas disk and then be left on polar orbits. Larger particles may be able to form after the gas disk has already become polar. So finally, it's worth considering the possibility for polar aligned circumbinary planets and why we haven't found any yet. So while all the observed circumbinary planets are currently coplanar, this is likely a result of selection effects. And this plot shows the misalignment angle as a function of the binary orbital period for circumbinary planets, disks, and debris disks. So alignment is clearly preferred around short orbital period binaries, while for larger orbital period, we can actually see a wide range of inclinations. The alignment timescale for a circumbinary disk increases with binary separation and at some point becomes longer than the lifetime of the disk. So as a result, we expect misaligned planets to be more likely around binaries with longer orbital period. This figure shows the binary eccentricity of solar type stars as a function of binary orbital period. The two binaries with polar disks are highlighted here, and they both have a very large orbital eccentricity. This red box shows the orbital period of the binaries around Kepler planets, the Kepler circumbinary planets. And you can see that the orbital periods are all relatively short. So it's not unexpected that the Kepler circumbinary planets are all close to alignment. Of course, it's also easier to find planets that are coplanar when we're using the transit method, since there's no nodal precession when they are coplanar. This means that they transit the stars on every orbit, whereas polar planets may potentially be found in the future with eclipse timing variations, perhaps. Now, this plot shows the stability of planets around a binary with a high eccentricity of 0.8. The y-axis is the inclination of the planet, and the x-axis shows the orbital separation. Now, the colored regions show planets that are stable, and in the white region, they're unstable. So for this high eccentricity, it's clear that the polar planets, meaning those that have an inclination close to 90 degrees, they're stable much closer to the binary than the coplanar planets. So given that we have observational evidence for polar gas and debris disks, we expect that planets will be found in the future. So in the last part of my talk, I'd like to consider briefly planet disk interactions for planets that form in a misaligned disk around one component of a binary. Similar effects would apply to planets that form in misaligned circumbinary disks as well. So if the planet mass is sufficiently small that it doesn't open a gap, then the disk and the planet can remain coplanar. However, if the planet is massive enough to open a gap, then we can get dynamically interesting effects to occur. The planet and the disk only remain coplanar to each other if the disk mass is very high, or if there is a very small gap size between the planet and the outer disk. This plot shows an example of the tilt oscillations that are driven as a result of planet-disk interactions. So we have a planet and an outer disk around one component of a binary. This is actually an analytic solution for an inviscid disk. The upper panels show the inclinations and the lower panels show the nodal phase angles. So in this case, you can see the planet and the disk are precessing independently. However, they're undergoing tilt oscillations. So they both begin at the same inclination, but the inclination of the planet initially increases while the disk initially decreases. This is a nodal secular resonance that drives inclination growth. So nodal secular resonances occur in the solar system caused by Saturn and Jupiter, and their effect is seen in the asteroid belt where strong vertical motions are driven. This plot is the same as the previous one, except the mass of the disk has been increased. And now you can see that the tilt oscillations of the planet have an even larger amplitude. And in this case, the nodal phase angles are locked, meaning that the planet and the disk are precessing on the same timescale. So irrespective of whether the nodal phase angles are locked, the planet and the disk are going to undergo these tilt oscillations. So now let's consider a hydrodynamic simulation of a massive disk around one component of a binary that's initially misaligned to the binary orbital plane by just 20 degrees. Now, the planet forms in the disk and is initially aligned with the disk. The planet and the disk undergo these tilt oscillations, and you can see this in the upper panel here, which shows the inclination of each as a function of time. So the planet inclination is shown in black, begins to increase, and the disk shown in blue begins to decrease. Now, the planet increases until it becomes above the critical angle required for Kozai-Lidov oscillations. So in the second panel, you can see that the planet's eccentricity increases. So even a disk that has just a small misalignment of 20 degrees through planet-disk interactions can lead to the formation of planets that become highly eccentric through these Kozai-Lidov oscillations. Now, multiple planets may even form around one component of a binary. The planets can carve out multiple gaps, and this leads to the disk being cut into disjoint rings. The images on the right show an example where there are two planets in a disk around the central star. There's also a binary companion that's not shown on this scale. So in this case, the evolution of the various parts, meaning the parts of the disk and the planets, they're much more chaotic. But similar overall effects can be seen as in the single planet case. So the tilt oscillations and the interactions can even lead planets to flip over to be closer to retrograde than to prograde. So these multi-planet disk interactions can lead to highly inclined planets. So we've seen that planet-disk interactions around one component of a binary can lead to the formation of both highly eccentric planets and also planets that may be highly inclined to the spin axis of their star. Observations of exoplanets show a wide range of eccentricity, as shown on the left, and also spin-orbit misalignments, as shown on the right. And neither of these are really seen in the solar system. So the effect of binaries can certainly help us to explain some of these properties. Some of the highly eccentric planets may be later circularized through tides, and this can lead to the formation of hot Jupiters. So in conclusion, I hope I've shown in this talk that misaligned disks and their interactions with planets play an important role in the planet formation process. Since most stars are in binaries, it's important that we understand how the torque from a binary companion affects both the evolution of the protoplanetary disk and the resulting planetary systems. So first, I showed that a detached circumplanetary disk has a disk aspect ratio and size that makes it unstable to tilting as a result of the tidal potential of the star. A misaligned circumplanetary disk with a spinning oblate planet align to each other on a relatively short timescale, and both then show an increase in tilt on a longer timescale. So even a slightly misaligned circumplanetary disk can lead to a primordial giant planet spin-orbit misalignment. Second, a highly misaligned disk around one component of a binary can be unstable to Kozai-Lidov oscillations, where the disk eccentricity and inclination are exchanged. The tilt of a circumplanetary disk may grow sufficiently that the disk becomes unstable to cozy off oscillations, and this may lead to episodic accretion onto the planet. These oscillations may also occur if a protoplanetary disk around one component of a binary forms at high inclination through stochastic processes such as turbulence during the star formation process. The cozy-off oscillations damp out unless there's a continuous source of high inclination material. But this may occur if there's a highly misaligned circumbinary disk feeding the formation of the circumstellar disks. Planet formation may proceed quite differently in an eccentric disk compared with a circular orbit disk. Third, a misaligned circumbinary disk can evolve to a polar state where it's perpendicular to the binary orbit. Polar circumbinary disks and planets may actually be even more common than coplanar planets and disks if they're around highly eccentric binaries. The Kepler planets are all found around relatively short orbital period binaries, and so it's not surprising that they are all coplanar. In the future, we expect to find misaligned planets around binaries with larger orbital period. And finally, planet-disk interactions around one component of a misaligned binary lead to tilt oscillations between the planet and the disk. These tilt oscillations can increase the inclination of the planet until it becomes cozy-off unstable. And this can lead to the formation of highly eccentric planets and highly inclined planets. So thank you very much for listening, and I look forward to seeing you at the conference. Thank you.